So let's talk about these four factors in a little more detail. The first, of course, is atomic structure. We talk about atomic structure. This really simply means how many valence electrons are in the atoms or in the molecules. And in the world of electricity, we categorize or classify materials in three broad categories. Those are conductors, insulators, and semiconductors. Now, the elements that we consider to be conductors are metals, and they all have in common the fact that they have either one or two valence electrons. And the elements that are considered to be good conductors are silver, gold, copper, and aluminum. Now, iron is also in the category or classification of conductors, but it's not in our top four list. Now, silver is the best conductor, gold second best, copper third best, and aluminum fourth best. However, copper is the most widely used conductor for a variety of reasons. One is that it's more prevalent, therefore it's less expensive. Copper is also very malleable, meaning it can be bent or shaped quite easily. Aluminum is a fairly good conductor. However, aluminum has some problems. One is that aluminum is very brittle, meaning if we bend it, it can fracture. Aluminum also has a tendency to oxidize, which can compromise the electrical connections. And the third reason is that aluminum has a relatively high coefficient of thermal expansion, meaning that when aluminum heats up, it expands, and when it cools down, it contracts. And this expansion and cooling down of the conductor can cause or compromise the electrical connection. Now, insulators have 8 or more valence electrons. With a filled valence shell, that means there's 8 electrons in the valence shell, it takes a lot of energy to knock an electron loose. Therefore, these have a very low ability to conduct current. Some elements or molecules, for example, polypropylene, because of its molecular structure, has 18 electrons in the outer orbit. Polypropylene makes an excellent insulator. Now, don't assume that insulators cannot conduct, because if enough potential difference is applied across an insulator, we can get the electrons to be knocked loose from these valence shells and conduct. So there is what we call a dielectric breakdown, where if the voltage is great enough, we can actually rip electrons loose from the valence orbit and cause conduction. Now, the third category are semiconductors, and semiconductors all have 4 valence electrons. And our semiconductor materials are silicon, germanium, carbon, and other group 14 elements. Now, because these semiconductor atoms have 4 electrons in the outer orbit, these atoms bond together through covalent bonding. And this topic will be covered in great detail in your semiconductor electronics course. But through covalent bonding, what happens is that each atom now has 8 electrons in the outer orbit. At room temperature, semiconductors are actually excellent insulators. But because of their chemical properties, they have a separate classification called semiconductor. Now, there's an equation that allows us to calculate the resistance of some material, some substance, and that equation is R resistance equals resistivity times length divided by cross-sectional area. Now, this symbol here is the Greek letter rho, standing for resistivity. Oops. And rho is measured in ohm meters. Now, a supplemental document will be provided under course resources that provides a the resistivity of selected materials at 25 degrees Celsius. So let's look at an example. Let's suppose that we have a 100-meter length of what's called AWG 14 copper wire. "14-gauge wires was commonly used in your homes for the lighting circuits and the non-kitchen receptacle. And 14-gauge wire has a diameter of 1.63 millimeters. And copper wire has a resistivity of 1.71 times 10 to the negative 8 ohm meters. So the resistance of this 100-meter length of wire, resistance would be 1.71 times 10 to the negative 8 ohm meters times the length, which is 100 meters, divided by the cross-sectional area, and the cross-sectional area is that area of the wire, which would be, of course, pi times 1.63 times 10 to the negative 3rd meters, oops, all that squared divided by 4, which would give us a total resistance of 0.818 ohms. So this is somewhat significant in that most people think of a conductor as having no resistance. However, conductors, as everything, have some resistance. The resistance is determined by 3 factors. the resistivity or atomic structure of the material, the length of the material, and the cross-sectional area. Now, the fourth factor that we need to discuss with regard to resistance is temperature. Let me pose a question. As temperature increases, does resistance increase or does resistance decrease? And regardless of your answer, you're right. It depends upon the material. Conductors have a positive temperature coefficient. What that means is that for conductors, as temperature increases, resistance will also increase. Now, depending upon the metal, this response can be fairly linear or it can be slightly nonlinear. Again, the supplemental handout that you'll find under course resources will provide information on this topic. Now, semiconductors have a negative temperature coefficient, meaning that as temperature increases, the resistance decreases. So these terms, positive temperature coefficient, negative temperature coefficient, simply describe the algebraic sign associated with the slope of a graph that shows us resistance as a function of temperature. So again, resistance, symbolized with the letter R, measured in ohms, is merely the opposition to current, and that's determined by the atomic structure, the length, the cross-sectional area, and the temperature of the material.